everyone else is. Cool. So I think I'll start. Today I'm going to talk more about how to write proofs for OpenDP. Day one was like how an analyst uses it. Day two is a more developer perspective. Day three is more proofwriting. So first off, I'm going to show today is where the proofs end up, where you can find them once they're added to the library. And so if you're just navigating the docs website, then go to API, click on API. They should show up on public APIs that are making some kind of stability or privacy guarantee. So long as they've been written and moved into main. I'll do an example. Count. It's kind of a go-to example. It's a simple proof. It kind of demonstrates the whole chain of things. So here in the API docs, the make count constructor has a link to a proof document. Click on that. It'll bring you into a LaTeX rendered PDF with the general structure that we use for our proofs. And I'll go into more detail on this later in the talk. The place where these proofs live is directly in the code, directly in the code base. So if you go to the OpenDP repo and navigate down into the Rust folder, into source, into transformations, down under count, there's a tech file located directly adjacent to the implementation of that constructor in Rust. And the tooling we have makes it so that when you have a tech file that proves a function in Rust, then it should automatically show up in the documentation.
Please increase the font size.
Yeah.
Wait, so how did you get to the proof document? I think I'm looking at it
Um,
wrong. Is it the API from Python?
yeah, search for make count.
This one?
Yeah. And then there's a link. Oh, then search for. Let's see it. Are you in? Oh, so what's happening here is the library version is 0.2. So this version of the docs doesn't have that yet. If you go to stable, which is what's currently out there, then the API documentation should have it.
Oh, gotcha. Okay, thank you.
Yep. So if you go to like old versions of the docs, then links may not exist yet.
Good to know.
All right, so then what is the process of adding more of these tech documents to the repo? Well, the way we go about it is you open a PR that adds the file and ask for reviews, and various people in the OpenDP ecosystem will come and leave comments and ask for changes or make questions. So
Is there a flag that people should, or tag that people should put on their PR, or do people are just looking at the repo and noticing things?
so typically what happens is I'll see it and request a review from someone.
Okay,
And I might, we've been recently adding more tags like for proofs.
Okay.
Like add a tag for it, or you might add a tag for it.
mechanism is kind of,
Yeah,
okay.
yeah. We're trying to keep things simple for people that want to contribute. So all the bookkeeping is stuff that we can handle. So you'll notice when a PR gets opened with a text file in it or a change to a text file, there's a automatic comment that shows up in the PR that shows the rendered file. And this will stay up to date with whatever tech is in your branch. The main thing is that we don't want to be checking in lots of binary files into the code base. So this keeps the repo size trim. It also makes it so that when you go and look at a rendered PDF file, the macros involved and in the tech can check to make sure that the code is up to date with the proof itself. So there's some extra macros I'll talk about in a minute where it'll go and check to make sure that no changes have been made to the code since when the proof has been written, and it'll notify you if there have been changes. So it self-reports if it goes out of date. If we were like checking those files in, then you'd never know. So this is the general process. This is another example where I had an update to a proof from before. Chuck left some comments asking why the changes. The diffs are pretty small here. We're keeping a log of the changes we make to proof files, try and stay open and transparent. So if in the rendered PDF, you can click through and see comments being made on changes to the proofs at any point in time. Here's another example of a proof that has been opened more recently. For randomized response, we have a whole bunch of PDFs included here for changed files. We can also write proofs and embed proofs for things written in Python, for example. Doesn't have to be just code implemented in Rust. If you're navigating the Rust docs, you can also see proofs for functions that are not made available in Python. So an example of this is the stack of samplers pulled from a discrete Gaussian paper from Snikey. This is bringing up the relevant pieces of that to prove the correctness of this function. So more proofs are available for viewing from Rust docs.
And there are these things that the Python code doesn't even have an indirect dependency on.
Yeah, so there is an indirect dependency somewhere along the way for make Gaussian.
Okay. So like if you just were on the Python side, you really wouldn't see all the things that tell you that the make Gaussian is proved. Okay.
Yeah, you can once the full chain is there, the full chain of dependencies is proven. You might click on a function from Python. There's links inside the PDF for that function in Python that take you down into proofs for its dependency.
Okay. Okay.
And you kind of navigate everything from the Rust docs, but you have an entry point from the Python docs.
Okay. And then there's links between groups. Okay.
Yep. So we set it so that the documentation for the Rust crate includes private functions for this reason, so that you can navigate. You can use it as an index to navigate through and find proof docs for everything. Okay, so what is a proof actually doing? What is the general structure we're using? There's this proof initiation docs page on the docs website. I'll kind of use that as a guide. You can pull it up yourself. And this text is really tiny. Better? Okay. Each document, each proof has a Hoare triple and a proof. So we're using a what's called Hoare logic to provide the general structure of what we're trying to prove. And a Hoare triple breaks down into three pieces. You have a precondition, a pseudocode, and a postcondition. The precondition and the pseudocode are necessary in order to prove the postcondition. So in this next part, when we prove it, what we're trying to do is say that the postcondition is true given these two pieces, assuming that these two pieces are what we're dealing with. Does that make sense? The pseudocode that we've been using has been it's pretty close to Python. It'd be nice if it were in a formal logic system, but we have not gotten to that point yet. There's some complications there that we talk about offline if you're interested. So what we ended up having is we have this proof doc with some pseudocode in it, and we also have the actual implementation itself. So there's essentially like two implementations of the same function. Pseudocode is obviously a little bit simpler. It's not runnable, but the motivation for having it is that we don't want to have to ask DP experts to understand Rust code when really we all need them to do is check proof and the logic of the program logic is correct. So let's do an example. We have this Rust function. The syntax for Rust is, if you think of it in terms of Python, fn is like def. This is the function name. And then in Python, you only have arguments. You don't have type arguments. In Rust, you also have a type argument here. So you can think of this whole block as type argument, or this whole block is just the arguments that you have for the function. You have an argument A, you have an argument B, and you have another argument, which is the type of A and B. And this function returns possibly an error or T. So then the body of this function is here. We're computing the absolute distance, so we take the difference between A and B and compute the absolute value. And this function does subtraction with rounding towards infinity. We've been very careful with how we do arithmetic in Rust. We have a lot of helper functions that control rounding of various mathematical operations. The little question mark says if the subtraction failed, then exit the function immediately. And then alerting abs will compute the absolute value. And if it's a data type where the absolute value doesn't exist, then it'll also throw an error. So some of the signed integers don't have, like if you take the absolute value of a signed integer, it sometimes can fail, which is a separate curiosity. So that's what's going on in this code here. There's a lot of explanation for a very small amount of code, but it's Rust, so the corresponding LaTeX code would roughly be structured like this. we have a sty file that brings in a bunch of macros that you can use to make writing the proof a little bit quicker. And it breaks down into two sections. We have the triple and we have the proof. A few macros that are in that sty file. You can mark a LaTeX file, LaTeX proof as contrib. Something that you'll notice that on the Python code, you have to enable a feature contrib. That that feature is set whenever the code itself has not been vetted, and there's a similar concept for proofs. A proof can be written, but still needs to pass the vetting process. So it should be marked as contrib if it is in that state. And this, yeah.
How does like the review, like would a proof ever still be contrib after the PR has been complete?
Yeah, so there's been cases where I'll write a proof and it'll get merged by Andy or someone else. And it hasn't been reviewed by, say, like Marco Gabordi or Salil.
Okay.
And it's marked as contrib.
Okay.
Yep.
So sort of tiers of.
Yep. So in the future, take another round and open a PR that removes contrib, the contrib flag, and get reviews from vetting board.
Okay, cool.
Yeah. These are making it possible to navigate two proofs for other functions, this /rust doc. So say I'm using a sampler in order to implement the Laplace mechanism. I can have a link to that, to the respective proof for that dependency. And this is a macro you can use to make it so that when you render the LaTeX file, it'll self-report if it's out of date. I think those are the big ones. Oh, this one's important too. Valid transformation, valid measurement. There's a common set of requirements for a measurement or a transformation to be considered valid or private or stable, respectively. And those requirements are listed out in this macro. All right. So in the case of this example, the precondition for absolute distance is that the data type T has some properties. You can also have preconditions that are not part of the type system. And when you're building this nested proof for a chain of dependencies, then you might say, I'm going to use this function, and I know that it's valid because I've proven that these properties exist for the arguments I'm passing to that function. And so it satisfies the preconditions of that proof. So we're just building up a system, a framework for proving in chains of function calls through these four triples. The pseudocode, as I mentioned, is pseudo Python. It's linted through our CI, so we try to check to make sure that some common sense things are checked, but it is not executable.
But I think that would only work if it's an included thing, like if it's
Right.
inline, like this example here, the Python linter can't see it, so the preferred thing is to have like a standalone Python.
Yeah, exactly what Chuck says. And then the post condition. So for this function, we might say for any setting of the input parameters for which the precondition holds, absolute distance returns either out, which is this mathematical expression, or an error. So when we're writing proofs, first assume the preconditions are met. And then if you actually write this out and try to prove it, you'll find that the code is not valid. It doesn't satisfy the post condition. In this case, if b is smaller than a and we do subtraction with rounding towards infinity, then it rounds up. So we have a negative number, we round up towards 0, and we end up getting an output that's smaller than the distance. We're looking for an upper bound on the distance. So like even in really simple cases where we have a function that looks naively looks very simple, the proof will potentially find issues in it. All right, and then I'm going to show the sty file, and I'm going to show proof for one of the actual constructor functions in the library. Any questions at this point? All right. So here's a make count tech file. It follows the same structure as the template from before. There's more preconditions on this this function. Some requirements on the type TIA. There's some requirements on the type TO. Luckily, there's no requirements on the arguments themselves. So essentially, all these preconditions can be checked by the compiler. We're saying that the type TIA, which is the type of inputs to make count, so make count takes in this case, a vector of values of type TIA. And we need to satisfy this trait. The output type needs to satisfy this trait and some additional requirements as well. Here's what the pseudocode can look like. It's Python-esque. There's some additional labels in here for linking to specific parts of the proof. We get down to the post condition. This is just calling a macro from the sty file because all transformations have the same requirements of them. I pull that sty file up. So like for a transformation to be valid, we have two requirements that assuming that the input to the function is in the input domain, then the output of the function is in the output domain. This is a necessary requirement in order to chain transformations together, or transformations and measurements. And a second requirement is the stability guarantee. For every pair of elements U and V, or adjacent data sets U and V in the input domain, and for every pair of input distance and output distance, then if U and V are close under the input metric, then the function applied to U and the function applied to V are D out close under the output metric. So things remain close. Measurements have one fewer requirement. All you need to do is prove the privacy guarantee. And the wording is essentially the same, but adjusted for distributions. So out here, we have the post condition being these two properties must be met on the transformation. And so we have two subproofs to prove these in turn. Oops. Yeah. So if I render that LaTeX, you end up getting a very lengthy expression like this, starting out with the distance between the outputs in terms of the output metric. We're going to make it bigger and bigger by breaking it down to smaller pieces until we've shown that it's less than or equal to D out, which is what the stability map provides. Any question on how this works?
Just Latin, right? No, it's not being very, like human is going to verify that.
Yeah, human verification. Yeah. It would be nice to have formal verification. I think there's some limitations on formal logic systems as to what they can prove in when it comes to DP guarantees, given the probabilistic nature. I think Chike might have more information about that. So ask him if you have questions on limitations of systems. But I think that there is a accessible subset of what we might want to prove to formal logic systems. So,
For example, in this pseudocode, you use like absinthe, right? Like you probably need to use its properties to prove something. So how do you know? How do you find the properties of this function? So,
you said I used absinthe.
like, right? Like.
Oh yeah.
So like,
Yeah, so that's like one of the major downsides of this is that you would need to have handwritten axioms for everything.
Yeah.
And that could also introduce bugs.
But if you want to find them, you need to go to the all PDFs and put that there.
Yes,
Okay.
but there's that macro that you can use to like click through and find that definition. And if you notice, if you look through the supporting functions throughout the traits module, and in general, you'll find that the doc strings in Rust all have proof definitions, like describing exactly what they're promising. So like we're not just trying to prove correctness of the public functions, the constructors. Also need to prove that the proof definition, the promises that supporting functions are making are also correct. So it's kind of hit and miss on which functions have proofs and which don't. But they're all set up so that they all have definitions that can be proven. So if I look for a proof definition, I have 154 definitions for various things. So there's our structure. It's it's somewhat formulaic. It's like, you know what you want to prove, you have a pretty good idea, how the proof would look and how it would work. And it's just hammering out lots of, very carefully written proofs.
Can you explain again how you did this linking or how you're going through like different files that quickly?
How am I going through different files this quickly?
Yeah, for example, let's say that you're here you want some other property of an object, right? That's linked to it. Maybe
Oh.
sample Bernoulli is not the best example, but
Oh, like maybe I want kilobytes.
yeah, something.
So if I'm playing around with it in IDE, I have
Yeah. No,
nice
so,
shortcuts
mean,
and stuff. But,
only for proofs, not for code. You're doing that in code and then
right. So in this proof, there's a slash rust doc macro in the tech for symmetric distance. If I click on that, it'll take me down into its definition. So it's somewhat up to the proofwriter to put some links in to make things easy to navigate. You'd say that it would be possible to automate that, but it's handwritten for now. And yeah, like in this case, I used impcast. I followed through to the Rust doc definition. There's a proof definition in here, and if I had the time, there would also be another link to a PDF file in here that you could look to validate that the implementation is correct. And this is what I mean when earlier when I was saying that the Rust docs are kind of a backbone for all the proofs, is that they give a structure that you can use to link things together. And that's why we're even including private things in the documentation, because private functions are also interesting if you're wanting to verify correctness.
How does the proof workflow relate to other flags? So like, you'd have proof, but sort of part of that proof is this is proved as long as whatever the user is on, or this is proved without, but I think we haven't done the flip point stuff, like other stuff.
Yeah. So in a deal world, you could say the flags that need to be set for any given function are pulled from the proof doc. But that's not really reasonable to do with the Rust build system. So that's also human verification.
So like, do the proof docs right now sort of say this is proving it up to this point?
Yeah, there's a number of proof docs that, well, there was a number of proof docs. I don't think we have very many now that had a flag for floating point.
Okay.
So there's just a macro you'd have in the top of the LaTeX file slash floating point, I think it was.
Okay.
And the respective Python and Rust code have that flag set. Any more questions about this? I think this pretty much wraps up what I was wanting to talk about. Cool. So this was a shorter session as I expected, and we don't have any chat comments, so I'll end this here.